So today we're going to start talking about Riemann sums, and however far we get, your homework is to finish the problems in this part of the packet, so the AP problems. And so we're going to just start kind of exploring this idea. So our goal is to estimate the area of the region bounded by f of x equals x squared plus 3, and the x-axis between 0 and 2. So you've got part of a parabola. You want the area between that and the x-axis, between these two values. So let's first sketch this. Remember part 1, let's kind of sketch this thing. So an x and a y axis. We're looking between x equals 0 and 2. So f of 0 is 3. Okay, so there's f of 0. And then 2, 1, 2 like this. F of 2 would be 7. 1, 2, 3, 4, 5, 6, 7. Space that out pretty well. And I know it's a piece of a parabola, so I'm going to curve that a bit. And then I'm just going to drop kind of a dotted line down here because I am looking at this region. Don't color this in with your pencil, but I'm looking at this region here. Okay? I'm trying to estimate that area. Now, this is not a nice polygon, like it's not a trapezoid with a linear side right there that I could just find the area of, so that's why we have to figure out kind of how to do this. What if we just used 2 rectangles? So then we would call those 2 sub-intervals. And in addition to knowing how many subintervals we have, which we call n, number of subintervals, we would also need to know what kind of sum do we want to use. So like if I use rectangles to estimate this area, I can find the area of a rectangle and say, yeah, there's going to be some space left over, but it's the area under this curve is about this much. So an example would be, maybe I start at this 0, 3 point, and I draw a little rectangle that connects over to when x equals 1. I can find the area of that rectangle. And then I can also connect a point for what f of 1 would be. And f of 1 would be 4, so that is that point. And I could draw a rectangle there, find that area, and say, well, I know the area under the curve is a little bit more than the area of these 2 rectangles. So I can kind of get that accurate. We could have upper sums, lower sums, and midpoint sums. This would be considered a lower sum because if you look at this, the area that I'm going to get is going to be lower than the actual area. Also, the rectangles are contained underneath the curve. So if I just use 2 rectangles to estimate the area, then the area would be about equal to, let's see, mark off these numbers so it's easier to look at. This first rectangle has a width of 1 times a height of 3. And the second area of a rectangle still has a width of 1 and it has a height of 4. So we're saying, well, we estimate the area to be about 7 units. I know that the actual area is more than that because I can see the missing space that I have. To kind of put some technical things in here, what is this 1 and this 3 and this 4? Let's put those in more general terms. The 1 turned out to be the width between my 2 little subintervals. The width of a subinterval, we call that delta x because it is the change in x values. So that's the width of each little subinterval. Remember, subintervals where we have 2 rectangles. And so delta x can always be found by just saying, in this case, it was like 1 minus 0, and we had 2 minus 1. So you're just finding the change in the x values. So sorry, I don't need to write anything extra there. In general, you could, actually, let's give a generic formula, sorry. In general, you could say, I'm going to take my entire section, let's call this A and this B. I could take my entire section that I'm interested in, B minus A, and divide that by the number of subintervals, n. So in this case, it's 2 minus 0 divided by 2. Tells me to place a rectangle every 1 unit. So in general, this formula is delta x, that's where the 1 came from. And then the 3 and the 4, those are function values, right? So this was f of 0 plus f of 4 was f of 1. And even though we have f of 2 on the map, we didn't use that for this lower sum. 2 rectangles is not very accurate. There's a lot of extra space here. There's nothing saying we have to use 2 subintervals. So what if we use more subintervals? You would think the more rectangles we use, the more accurate we're going to get. So let's try n equals 4 subintervals. So I want to sketch the same graph. I'm going to lower it a little bit. So we had f of 0 was 3, f of 1 was 4, f of 2 was 7 here. My spacing's a little off on that. All right, so instead of 2 rectangles, we need 4. So if we're having a hard time picturing that, our delta x is still 2 minus 0, but now we're dividing it by 4 subintervals. We want 4 rectangles. So that means that every 1/2 of a unit, we should be putting a rectangle. Okay, so there, at 1/2, at 1, at, I spaced this out a little weird, at 3/2. And then we're doing a lower sum. In this case, it's a left sum, thinking the point on the rectangle connects to the left side of the interval and connects over here. So my first rectangle has a height of 3 and a width of 1/2. My second rectangle, its point is on the graph at whatever f of 1/2 is, and then it goes across. My third rectangle is at f of 1. And my fourth rectangle is at f of 3/2. We're still underestimating the area, but we're doing a little bit better. There's not as much blank space as we had before. So this area underneath the curve would be approximately, the subintervals are all a width of 1/2, right? You have a 1/2 times the first height, which is f of 0, plus, it's going to be another 1/2 times f of 1/2, but why don't we just go ahead and put a 1/2 out here, factor it out kind of, and then add the heights of our 4 rectangles, right? Because that would be 1/2 times the height of the first rectangle plus 1/2 times the height of the second. So I'm going to say f of 1/2 plus the next rectangle is at f of 1 plus the last rectangle has a height of f of 3/2. So notice when you're doing a lower sum, or in this case a left sum, that you include the left side of the interval, and the right side of the interval, the f of 2, never makes it into your sum because you're not using that point. If you do, you'd be outside of the range of interest. All right, so what is this equal to? This is 1/2 times, we said f of 0 was 3. We haven't found f of 1/2 yet. Let's see. It's 1/2 squared, so 1/4 plus 3, so 3 1/4, or 13/4. 1 was 4. 9/4 plus 2 plus 3, so 9/4 plus 12/4 is 21/4. In interest of time, I do have this calculated ahead of time just so that we don't have to take forever. So if you want to pause me at this moment so you can calculate and check, it's 7 plus 8.5, basically. So I've got 1/2 times 31/2, 31/4. Now, we don't normally change to mixed numbers, but I think it's worth noting that's 7 3/4. So our area with 2 subintervals was like, it's about 7. Now we got a little bit higher, right? Now we're saying, it's about 7 3/4 square units, whatever they are. So let's look at another example, a different graph. This graph might not be popping up very well on your notes, but approximate the area bounded by y equals 1/4 x squared plus 1 and the x-axis using 4 subintervals and a lower sum on the interval 0 to 4. Okay, so the curve is right here. I do not know if you can see this, or maybe I've deleted it from the blank copy, but at 0, there is a point at 1, and we're supposed to go out to 4. 1, 2, 3, oh my gosh, 1, 2, 3, 4, I think is right here. And if I plug 4 in, 4 squared is 16, divided by 4 is 4 plus 1 is 5. 1, 2, 3, 4, 5. We're just going to call that 5. It's very hard to see. So we're interested in this area of this little shape. All right, the first thing I like to find is my delta x. Delta x is the interval 4 minus 0 divided into 4 subintervals. That means 1 unit each. So our rectangles, the left side of your rectangle, wow, I'm really off here with my sizing, sorry. The left side of my rectangle should be touching the curve, and I won't have the height of f of 4 for anything. So the area is approximately equal to, just in general, it's a good idea to show, like, you don't want to jump right to your numbers. If I were doing this on a free response, I would show that my delta x is 1. So you could show like 1, or you could even write delta x right there. It's 1 times your adding the height of these 4 rectangles. Remember, the first height for a lower sum, which in this case is also a left sum because because the left side of the rectangle is touching the curve. It starts at, we don't have f here, so I'm going to say y of 0 plus y of 1 plus y of 2, oops, plus y of 3. It's a good idea to write that out anyway, just to organize your own work so that you don't accidentally use y of 4 or something like that. And you can see clearly that you do have 4 numbers here. So, okay, I don't need the 1 anymore. When I plug 0 into this, I get 1. When I plug 1 into this, I get 5/4. When I plug in 2, I get 1 plus 1 is 2. When I plug in 3, 9/4 plus 4/4 is 13/4. And again, just to save a little bit of time, I do have this written down ahead of time, so you can pause me if you want to calculate on your own. Make sure you get the same answer. But I'm getting 30/4, which simplifies to 15/2. So we're saying 7.5, right? We're saying the area under this curve is 7.5. Now remember, this is a different equation than what we first used, so we're not comparing it to these previous two. Repeat this problem using an upper sum with 4 subintervals. So an upper sum, I'm going to sketch this graph bigger. I don't know why I committed to that small one. So 1, 2, 3, 4. At 0, we hit 1. At 2, we hit 2. 1. Boom, boom. At 4, the height of that was 5. 3, 4, 5. Let's just get a nicer graph on there. So there we go. So an upper sum is going to be an overestimate. An upper sum, we should have some part of the rectangle above the curve or outside of the curve. So an upper sum, if you mark off where the section ends at 4, start on the 4 side. It's an upper sum, start on the right side of the interval. And our delta x, we're still talking about 4 subintervals, so it's still just 1 unit. But we're starting at a height of f of 4, or y of 4, and we're drawing that rectangle over to 1 unit across. So we're going to use this area to estimate the area above the curve, above and under in this case. And then we connect a point at 3 and draw a rectangle that goes through 2. There's that. And then we're going to use the height of 2, connect over to 1. And then we're going to land on 1 and connect over to 0. All of those rectangles are slightly above the curve, some more so than others. And so I know whatever area I get here is going to be larger than the actual area. But again, we're just estimating. So I, again, would show that my delta x is 1, and then I'm multiplying that width times the height of each rectangle. And the height of each rectangle, it doesn't matter if you start on the right or the left. I like to keep these in numerical order. So it's f of 1 plus f of 2. Oh, sorry, not f, y. Y of 1 plus y of 2 plus y of 3 plus y of 4. Some people prefer to make it 4, 3, 2, 1. It doesn't matter as long as you have the 4 terms there. That might help you kind of match how you drew it. And then I don't need the 1 anymore, but area, I should be using approximately equal to symbols. Y of 1 was 2. Y of 2 was 13 over 4. No, it wasn't. Y of 1 was 5/4, excuse me. Y of 2 was 2. Y of 3 was 13 over 4. Y of 4 we figured out to graph this was 5. And again, I've calculated this ahead of time, so you can pause and kind of do your math for a minute. Should come out to 46 over 4, which is about equal to 23 over 2. So using these are called Riemann sums, named after the guy who, his last name, who kind of thought these up or invented them, I guess you could say. We don't know what the actual area is, but we do know some boundaries for the actual area. We know that the actual area is, even though I know it's not equal to, I'm going to use this, less than or equal to 23 over 2. But it is greater than or equal to 15 over 2. So the actual area is anywhere between, 7.5 and 11.5, right? So quite a range. Not super accurate, but it's a good starting point. We have a lower sum where the rectangles are underneath the curve, and it's an underestimate. We have an upper sum where we have an overestimate because the rectangles go outside of the curve. You could also use a midpoint sum, which is going to sort of split the difference, basically. So let's draw this graph one more time. We're talking about that same curve. 1, 2, 3, 4, 5. So at 4, it hits 5. At 0, it was 1. At 2, it was 2. Sorry. Check that equation again. Draw in the curve. So what's a midpoint sum? Well, you still have 4 subintervals. So you're still figuring out, okay, the width of each rectangle is still 1 unit. So I still have a width of 1 unit, and I like to, for midpoint sum, let's just go ahead and every 1 unit put a vertical line. Now, when you're talking about a midpoint, the point where the rectangle touches the curve should be the center of the rectangle. So, for example, between 0 and 1 is the point at 1/2. So y of 1/2 is the height of that first rectangle. And part of it will be outside of the curve and part of it will be under. So area is approximately equal to our delta x, which is 1, times y of 1/2. The next one would be at 1.5. At this point, the left side of the rectangle is out, but the right side is underneath, and that kind of looks symmetric to me. So for each part that we overestimate, we kind of underestimate a similar part. So that was plus y of 3 over 2. Plus the next one would be at 2.5. So y of 5 over 2. And our final rectangle will be at 3.5. So that's y of 7/2. So you need to plug these fractions in. Again, in interest of time, I've gone ahead and done this ahead of time. So I'm going to drop the 1. 1/2 should have become 17/16 plus 25/16 plus 41/16 plus 65/16. Now, I believe I used a calculator at this point. I mean, yes, we can do all of these fractions in this math, but for Riemann sums, they're usually a little bit nicer to you on the real AP test. Our bookwork might be a different story, but anyway, if I calculate all of this, I got 9.25. And I know that's a good sign because remember back here we said the actual area is somewhere between 7.5 and 11.5, and 9.25 falls somewhere in between there. So that's a good sign. All right, so pause my video and find the lower sum, the upper sum, and the midpoint sum for this f of x. And if you want to check as you go in class, we're going to do the lower and then stop and check that before we move on to upper and midpoint. So lower first. You don't have to sketch this if you don't want to, although I kind of like to sketch it. So at 1, we're at 3. And then at 9, we're at 5. I like to have the visual. So delta x is 9 minus 1 divided into 4 subintervals. 8 divided by 4 is 2. So between 1 and 9, I'm using every 2 units. So like 3, 5, 7, and then 9. So these are the subintervals. And then I'm not going to draw the rectangles in every time, but that's just going to keep my mind straight here. And go ahead and use a calculator to make things a little bit faster if you want to. So for the lower sum, we've got 2 outside of parentheses. Now a lower sum would start at the beginning of the interval, so f of 1 plus f of 3, because that's the next interval, plus f of 5 plus f of 7. And I have 4 numbers there, so I'm finished at that point. Now I just need to sub in the values. So 3 plus radical 3 plus 2 plus radical 5 plus 2, radical 7 plus 2. I'm going to leave my answer exact here. All those numbers add up to 9 plus radical 3 plus radical 5 plus radical 7. So that is our lower area. If this were on a calculator part, you could go ahead and approximate that. Let's do, we'll do upper next. Just keep it in the same order. So upper. You have the same delta x. It's still 2. So the area starts off the same way. It still starts at 2. And if you want, let's do it this way. It's an upper sum. So why don't we go ahead and just write our first one as the right side here, like f of 9. You don't have to do that, but it might be kind of a good way to make sure you're not including points you shouldn't be. F of 9, f of 7, f of 5, and end at f of 3. Again, in interest of time, plugging in all of these values and simplifying, it should come out to 2 times 11 plus radical 3 plus radical 5 plus radical 7. Hopefully we find this value in a calculator to be larger than the lower. And then finally we can do midpoint. This is where I do like to have my picture here. because it's easier for me to see like, oh yeah, the midpoint is 2, 4, 6, 8. Picture's not required and not always easy to make, but in this case, it's okay. So my area is going to be approximately 2 times, I'm going to start back at the beginning now that I've marked that off, f of 2 plus f of 4 plus f of 6 plus f of 8. So remember, when you're doing this work, especially if you're not actually drawing the picture, when it says 4 subintervals, you should just have 4 terms added together. You shouldn't have a fifth or somehow only have 3. All right, so final answer for this one after you find these and combine like terms should have been 2 times 10 plus 3 radical 2 plus radical 6. All right, so we've been using rectangles. Another way to approximate the area under a curve is to use trapezoids instead of rectangles. Because if you think about it, trapezoids have that nice curved side, right? Like if you just draw some, just give yourself a generic curve here and some subintervals to do like that. A trapezoid would be pretty nice because in some cases it's going to fit really close to that curve. Here, here, here. The parallel sides are the distance between the subintervals, right? So that would be pretty accurate. You do need to remember how to find the area of a trapezoid. Area of a trapezoid is 1/2 the height times the sum of the bases. Now for us, the height of the trapezoid is always the perpendicular distance between the 2 parallel sides. So for us, the height is delta x every time. And then the sum of the bases will be function values. So I'm just going to write, I don't know, f of a1 plus f of a2. Because I don't know, those would vary between each thing. But it would be like 1/2 times 1 times f of 0 plus f of 1 plus 1/2 times 1 times f of 1 plus f of 2, et cetera, et cetera. So let's use that 1/4 x squared plus 1 graph again. I'm going to sketch that again. It was on the interval 0 to 4. So 1, 2, 3, 4. At 4, this became 5. Oh, I didn't. Sorry. That's going to bother me that that's not right on that line. Okay. 1, 2, 3, 4. That was at 1, 2, 3, 4, 5. So right here, 0 was 1, 2 was 2. Curve. Sketch. So use 4 subintervals. Delta x is still 4 minus 0 over 4. So here are the 4 subintervals. I'm marking them off every 1 unit. Now use trapezoids. So trapezoids would be connecting these first 2 points. The first trapezoid has a 1/2 times a delta x of 1. And then it's going to be the sum of these 2 bases. So this base is at f of 0, and this one has a height of f of 1. So f of 0 plus f of 1. And then you're going to have another 1/2 plus 1/2 times 1 times the sum of the next 2 bases. Well, the next trapezoid has one base at f of 1 and the other at f of 2. So that's another f of 1 plus f of 2. Now, I want to simplify things a little bit, so I'm not going to write all of this out right now. All of these little trapezoid areas are going to have a 1/2 times 1. So let's factor that out. And then let's just put in brackets all of these different little things we're going to have. We're going to have a single f of 0, right, because that was the beginning. But then f of 1 shows up twice. It shows up as the second base in the first trapezoid and the first base in the second trapezoid. So you're going to have plus 2 of these f of 1s. The same thing's going to happen with f of 2, right? Because here f of 2 got used in the end of this trapezoid, and here it is again, beginning of the next one. So you're going to have plus 2 times f of 2. plus f of 3 is going to get used twice because here it is in this trapezoid, and it also shows up at the beginning of the last trapezoid. You're going to have two f of 3s. Plus the final base was at f of 4. Now, I know that we have more than 4 terms, but remember, 2, 4, 6, we have 8 terms total, right? 2, 4, 6, and then these two are 8. We have 4 subintervals. We have 8 terms total because each trapezoid has 2 terms to it. So you're still following that rule, but you don't worry about the fact that, like, wait, I thought I was only supposed to have 4 numbers. You have 4 sums. If you write it out like this, you would have 4 chunks of terms. And again, in interest of time, I went ahead and calculated this ahead of time. Oh, but my answer got cut off. So I guess I don't have an interest of time. We have 1/2 times, this is 1 plus 10/4 plus 4 plus 13/2 plus 5. I am going to, since I'm almost out of time before class starts, I am going to do this. So 0.5 times 1 plus 10/4 plus 4 plus 13/2 plus 5, 9.5. So using trapezoids instead of rectangles, we got 9.5. And remember, our best estimate was probably the midpoint sum, 9.25. So now we're narrowing it down even more, somewhere between 9.25 and 9.5. Oh, actually, that is all that we're going to do together in class. The rest of this assignment is your homework. So, oh, I hope I didn't just, hopefully this isn't filled out for you. But if it is, one of them's done already for you. We do need to look at this one. And then your homework is to finish all of these. So you might have been lucky. I don't know if your blank packet has that one filled out already. But if it does, at least look at it to see what the heck I was doing. All right, that's it for today.